This is lecture 9A for Calculus 2. It is on the organization of the lectures for differential equations. This lecture was just some basic vocabulary. I suggest you write down every one of those terms: autonomous, linear, nonlinear. Give yourself a definition, and after that give an example, because you need to get a handle on the different types of differential equations before you can move to their solution. That's all that was given here. After this, I'm going to go through several examples, but instead of following the pattern of Stewart, in which he and Thomas also, in which they use these differential equations from different fields to sort of back up, to use them as examples, I'm doing the following. I'm grouping all of the equations for the RLC circuit in one lecture, all of the equations for the mixing problems in another lecture, all of the equations for the population dynamics in another lecture. I think hopefully that will be useful to you. If you go on into say some kind of biological field, you might want to make use of all those models for population dynamics. So I put them all in one lecture. Hopefully they'll be of use to you. You can go through, check them out, see how we obtain their solution, and maybe apply it to problems in your area. If you go into electrical engineering, you might be looking mainly at those RLC circuits in certain classes. So I group them according to the topic, and then within that topic I solve the equations using the various methods. We haven't gotten to the methods yet. So here's a summary of what I did. This was an introduction, and this introduction contains mainly vocabulary. What is a differential equation? What does it mean by a general solution or particular solution? What are initial value problems, boundary value problems, and then the various classifications: ordinary versus partial differential equation. What is the order? Is it linear or nonlinear, autonomous, homogeneous, or non-homogeneous? So all that has been included in this introduction. Again, not a lot of examples, but just vocabulary. In lecture number 2, I'm going to look at the direction or the slope fields for these differential equations, and that gives an insight into the solution of many of these differential equations. The ones we're going to study here, it gives you a lot of insight. Then I'll run through in lecture 3 the method of solution. This is a little long, but I want to put all the methods in one place. These methods are the integrating factor. That's used for first order linear ordinary differential equations. Then separable equations and the methods of solving them. Those are first order linear and nonlinear ordinary differential equations. Euler's method is a numerical method. And then a short discussion of changing second order equations into first order, because all of these, as you see, are for first order. First order. Okay, first order, and again first order. Well, what if we have a second order? Can we change it into a first order and then solve it by these methods? Really, we only have 2 methods. They're sort of related: use of integrating factor and the separable equations. Okay, those are really only the 2 methods. Okay, so this is method number 1, this is method number 2. Euler's method is numerical. Okay. After that, the lectures are divided on according to field of study. So there's the electrical RL and RC series circuits. The RLC circuit is not studied in this class. Not that it's not important, it just isn't studied here. Only the circuits that contain a series, resistor and an inductor in series, and a resistance and capacitance in series. Then there are mixing equations. That will be the flow of fluids in and out of tanks or in and out of rooms. Draining tanks, Torricelli's law. Okay. The next is motion with resistance, such as air resistance. In this, in that lecture, we look at the derivation of the equation governing like terminal velocity. Right. And then there's population equations. I just went through sort of showing you the different, from the very basic population equation to more elaborate population equations. Now, in both textbooks, Thomas and in Stewart, they discuss the predator-prey models. You can read about those in the textbook. They are solved there approximately. I'm not going to talk about them. They're very interesting, but actually to really study them, you need to have some, start using some numerical methods and getting into really how to solve these very important equations. But for this class, I'm not going to talk about them.